Thank you and good evening. I can imagine you guys are very tired at this point in the day. And the good news is for you is that I will be showing a lot of interesting pictures and not focusing too much on complicated formulas. So I'm going to be talking a lot about qualitative features of relativistic Euler. And full disclosure, when you actually want to study these things and do the PDE analysis, it can be quite involved. But nonetheless, all of the complicated analysis is motivated by very tangible and inspiring pictures. And so that's what I view as the heart of the talk today. And even though this is supposed to be the second half, lectures 3 and 4, we never really the last part of lecture 2. So that's where I'm going to begin with a recap from last time. Just quickly, to review, I had discussed that if you look at the relativistic Euler equations on the Minkowski background, and you look at within the class of plane symmetric and isentropic solutions, then by introducing a pair of null vector fields, L and L bar, which have explicit formulas, depending on the fluid equation of state, but which I'm only writing schematically here. And this is supposed to be understood. So this dt and d1 is with respect to the, so these differential operators are partial derivatives with respect to standard Minkowski rectangular coordinates on the Minkowski space. And by introducing L and L bar and R plus and R minus, these Riemann invariants, which completely determine the fluid in this symmetry class, you can reduce the flow to the study of two coupled quasi-linear transport equations where there are two transport directions. It's the L direction and the L bar direction. And one can even look to a simpler symmetry class where one of the Riemann invariants, let's say R minus, is 0 for all time. So that's a condition that's propagated by the flow if it's present in the initial data. So if you have only R plus active, that's called a simple solution. And as I was already trying to show you at the end of last time, you can discover a lot of exciting phenomena, even within this very simple symmetry class. And one way forward, the most fruitful way forward, as we talked about last time, is you can introduce an iconal function, U, which is basically the method of characteristics, and it solves a transport equation. So in plane symmetry, remember this operator L is predetermined. So this is really a linear transport equation for U. Away from plane symmetry, you have to solve the iconal equation, which is fully nonlinear hyperbolic. That's a serious complication. But in any case, you can in symmetry, and as always, you have to choose initial data for your characteristic function. I prefer to pick at time 0 the data to be minus x1. That's just useful for orientation. And then in TU coordinates, which I call geometric, L is just the partial derivative with respect to time at fixed U. Okay, and using this setup, one can sort of explicitly solve the equations. One can introduce geometric quantities such as mu, which measures, it's reciprocal, 1 over mu, measures the density of the characteristics in Minkowski space. Some of you may know this by a different name from other literature. This is also known as the null lapse in a different but equivalent context. And then the formation of a singularity coincides with the vanishing of mu, or equivalently the bunching up of the characteristics, or equivalently the blow up of the first derivative of the iconal function U with respect to, let's say, D1, the Minkowski D1. Okay, and then I proceeded to introduce a model problem where you can really get your hands on it. So this is a model problem within the simple class, or within the class of simple solutions. So here we have only R plus, a single Riemann invariant. And just for convenience, I took the operator L to look like this. It's dt, and then instead of being plus d1, the coefficient is 1 plus r plus. And you should think that I'm looking in a regime where R plus is not too big, but its derivatives can be, interestingly large. And similarly, you can define, this is just sort of schematically to show you what's going on. I introduced the other direction L bar. This is really just a definition in this setting. This is how I define it in the context of this model problem. And you don't really need L bar at this point in the analysis, because this is a system that doesn't have any other direction besides L. The purpose of introducing L bar is to show you in a picture issues that you have to be concerned about if you were looking at the solutions where both Riemann invariants are present. Okay. It's very convenient to choose some explicit initial data to show you what's going on. It's totally not important that you pick data that are this explicit. But nonetheless, this was my choice. At time 0, I choose data that's minus x1 over 3. And recalling that x1 is the opposite of u, it can be written in terms of u as follows. And then I wanted to show you what the solution looks like for this model problem for this choice of data. And even though this is a model problem, you can run the same R for essentially any relativistic fluid you want in simple plane symmetry. The fact that I've explicitly chosen these coefficients to be as such is totally irrelevant. It doesn't alter qualitatively the conclusions in the slightest. Okay. So there's this notion of singular set, which you have to be careful about how you think about what it means to describe the singular set, because we have two different coordinate systems. We have TU, which is kind of like an artificial coordinate system comprised of characteristic curves that we've chosen to introduce so that we can do analysis. But at the end of the day, let's say the real physical space-time is the Minkowski space. Okay, and in this problem, we're thinking of the differential structure of Minkowski space, and the ambient rectangular coordinates as being fixed, like pre-specified. Like they're the real, somehow that's the real differential structure in the problem, and this TU differential structure is just for convenience. Okay, but in any case, for that choice of initial data, you can solve the solution R plus. It doesn't depend on T, so you just write it down immediately in characteristic coordinates, and you can solve for mu. And remember, the vanishing of mu is where all the interesting stuff happens. You get these nice explicit formulas, and you can write down the level set mu equals 0 explicitly in terms as a graph. So T is a function of u, and here's what it looks like. And now one asks the important question: how do you translate from these characteristic coordinates back to the Minkowski picture? Okay, and the way we're thinking in this setup is that T and x1, so these rectangular coordinates, if you want, can be expressed as functions of T and U. So in other words, you can do the change of variables. You can go from TU space to TX1 space. And you can try to make sense of this curve, mu equals 0, in TX1 space. And for this particular simple explicit model solution, you can do this explicitly. In TX1 space, you can parameterize the curve mu equals 0 with respect to U. And remember, I'm looking at the range, U goes from -1 to 1. And here's explicitly what this curve looks like. And it has a cusp. It splits into two pieces. There on the next screen, I'll show the slide from the end of last time. There's a red half and a green half. So like one of the halves corresponds to U going from 0 to 1, and the other half corresponds to U going from 0 to -1. Okay. And here is the situation. So the red and green curve. So I had to memorize this picture because I'm a little colorblind. So I'm going to do my best to sort of get the colors right, but if something sounds crazy, it could be me. Okay, so here's the picture. As you start from u equals -1, and I'm going to trace with the cursor the mu equals 0 curve. As you start from u equals -1 and you start increasing it, you go to this green curve and you get to this cusp, and now you start increasing it again from 0 to 1, and you come up along this red curve. Now this entire piece is supposed to be viewed as red, but it's covered up a little bit by these pink straight lines. So what are these? What are these pink straight lines? These pink straight lines are in fact the integral curves of L. So these are the characteristics. And what you see is that they are impinging on the red curve. They're piling up. Their density is becoming infinite, and in fact they're all tangent to the red curve. And qualitatively, that's an part of the problem, especially away from symmetry. And similarly, on the other side of the picture, these black lines are also characteristics of L, and they're impinging on this green line here, and they're also tangent to it. You know, they touch tangentially. And then the yellow characteristic in the middle. So this is also a characteristic, and it's the dividing line. It's the unique characteristic that hits this cusp up here. So it separates things. And let's forget about this blue curve for a second, because this represents the L bar direction, which is not particular at the moment. So let's just ignore this. So how do we think about this picture? What is so special about this green curve and this red curve? These are points in space-time where a singularity happens. In other words, if you use the method of characteristics, let's say that you start studying the R plus solution variable by following the method of characteristics along the pink curves. You'll find the first derivatives of R plus with respect to D1, Minkowski D1, they blow up. You know, there's a real singularity here all along this red curve. Now, on the other hand, if you can run the same argument coming from the other side, if you study the characteristics in this part of the picture, they will bunch up on the green curve, and you will see that D1 of R plus also blows up the green curve. So if you want, the method of characteristics tells you that you have a singularity on the green curve, and you also have a singularity on the red curve, but coming from a different place in space-time. And so now you're faced with a very interesting philosophical question. If you're given initial data down here, like at time 0, and you want to understand the mathematical question, is the largest classical solution determined uniquely by the data, or determined by the data? You know, what is the largest classical solution? You know, roughly you want to call this something like a maximal development. You're faced with a difficulty. So this setup exhibits essentially non-uniqueness of maximal developments. And I can say exactly what's going on. I can show you what the difficulty is. Let's say that you study the portion of the initial data to the right of 0 in this picture, so along this part of the line. If you do that, you can determine the solution everywhere in the region to the right of the yellow curve. So you can follow the solution all the way up to the green curve, and you see that this is where the first singularity forms, if you want, or this is the singular set. In particular, you don't see this red singular curve at all if you're studying only the portion of the data coming from you know, to the right of 0, because this part of the singular curve is generated by, you know, initial way over here, and you won't even see it until these characteristics from over here have a chance to impinge right here. So in other words, this red curve, if you study the initial data to the right of 0, is really not there. It's really not there. So this picture is basically symmetric and the initial data were odd. So you can run the same argument to the left. So if you take initial data that lives to the left of the yellow line and you look what's going on from these characteristics, you'll impinge on the red line, and you see a singularity only on the red line, but you don't see a singularity on the green line, because this green line, corresponds to what's going on in a totally different solution regime. So, you're faced with a real dilemma. Where is what is going on? And the real difficulty is that you in fact have non-uniqueness of a maximal development in this situation. There's sort of a lot I can say about this picture. If you want to sort of learn about these ideas, like, what can go wrong, how can you have non-uniqueness of maximal developments? There is a beautiful paper by, what's her name? Eperon, Rial, and Sibersky from a few years ago, where they were looking at similar phenomena in a more complicated context. They were looking at the, amusingly, they were looking at, it's a different equation. It's connected to the minimal, time-like minimal surface equation. It's connected to what's called the Born-Infeld equation. They were also looking in symmetry. So they were sort of the first ones to understand that you can have non-uniqueness of maximal development for these kinds of equations. Let me just sort of qualitatively tell you what's going on. So the basic issue is that let's say that you look, let's ignore the green, let's just say, for sake of argument, you ignore the red curve, right? You say, I want to study the part of the solution where you have a singularity forming from the collapse of these black lines on this green curve. Okay, and then I study the part of the solution where you have these pink curves, but I don't look past the green curve. In particular, I don't go into this region where the red curve, I don't follow these pink characteristics region where the red curve is. I sort of stop looking once I get to this green curve from the left. So what happens in this situation? If you ignore this red curve and you don't follow those pink characteristics far enough, follow the black ones long enough to see a singularity, what happens is that you have this singular boundary, this green curve, just call it a singular boundary, but you have like a classical solution, part of what you would like to call the maximal development on either side of it. So you have, like, below the green curve, there's no singularity because you're ignoring this red curve because you're saying the impingement hasn't happened yet. So you have a classical solution here, but then you also have a class on this side because these pink characteristics haven't crossed into the region where you can see the singularity forming there. So you have a classical solution on both sides of what you'd like to call the singular boundary. And qualitatively, that kind of criterion was identified in the paper by Eperon, Rial, and Sibersky as being a serious obstruction to uniqueness of maximal classical developments. So basically, if the solution wants to live on both sides of what you would like to call the singular boundary, then it's very likely to have non-uniqueness of maximal classical developments. And so I'm showing you this can happen in fluid mechanics. I mean, this really happens. You can do this for compressible Euler. You can do this for relativistic Euler. You can do this basically for almost any wave equation in 1+1 dimensions that you write down. So, okay, sort of the semi-linear terms. If you consider arbitrary wave equations with, bad semi-linear terms, that may mess up the analysis. So don't take me too literally every wave equation. But let's just say large families of wave equations will exhibit this same phenomenon. And I haven't seen, aside from that paper that I mentioned, I haven't seen these arguments sort of written down carefully or even explained or referred to anywhere. And I will tell you why. Because these pictures are usually drawn in the context of textbooks on, let's say, nonlinear hyperbolic conservation laws. And for that community, the second you have a classical singularity, they want to go to the weak formulation, and they're not interested necessarily in questions about maximal classical development, because the second they see the singularity, they want to switch to a weak formulation and solve the flow using the weak formulation starting from the first cusp, if you want. And that's great because that procedure works very well in one space dimension. There's a developed theory for unique weak solutions for Burgers-like equations. It's very classical by now. However, as soon as you leave the world of one space dimension, if you want to have a good theory for solving somehow uniquely weakly past what you would call the first singularity, you really need to understand this picture. You really need to grapple with this non-uniqueness and how it screws up the evolution or it doesn't. And you also need to understand, how can you recover uniqueness and, what's going on. And so here's the short version of the story. For wave, let's call this like a non-generic solution, even in 1+1 dimensions, because the wave is simple. And sort of generically within the space of all 1+1 dimensional solutions, the wave is not going to be simple. There's also going to be R minus. So what happens? As soon as you have a cusp or a first singularity, so this is the lowest point where the green and red curves touch, that lowest point is properly the first singular point. Sort of generically, you have to remove the light cone from the evolution. Okay, you have to worry about the singular behavior in the in the R minus variable. You have to worry about the rest of the system if you want. You can't just when you're thinking about whether classical solutions exist, you can't just think about the L direction and R plus. You have to think about the other directions. So it turns out for this particular class of problems, there's enough regularity, directionally dependent regularity, so that you can actually define the characteristic in the other direction, the L bar characteristic that shoots out of the lower cusp and goes in the other direction. Okay, and that's essentially a Cauchy horizon. And even though in this part of the let's say that if you rightfully want to call this a Cauchy horizon because it's a null hypersurface that shoots out of the singularity, you really want to say that generically this is going to be a boundary of space-time that you can't uniquely extend the solution past. Okay, now obviously that can't be true literally because I'm just giving you these examples where you can extend past the Cauchy horizon. These pink curves go right through it without any problem, but that is very non-generic in the sense that you have only the R plus variable active in this picture. The second you have to worry about R minus, it becomes an interesting qualitative, well, not just interesting, like crucial qualitative question, can you extend the solution uniquely past the Cauchy horizon and so forth. So in other words, the point is that for generic solutions, you do have to sort of worry about the Cauchy horizon, and it will be a boundary beyond which you can't extend uniquely. Okay, and point for purposes of Euler and wave equations is that this Cauchy horizon that shoots out of the singularity cuts off these pink curves. Okay, it cuts them off. So these pink curves really talking about maximal classical development. For generic solutions, they're not going to be allowed to pass through the blue curve. Okay, that's going to be a boundary, and therefore this red curve is not part of your maximal classical development. So for generic solutions, you may expect to recover uniqueness, and for generic solutions, this red curve should sort of not really be part of what you would like to call the maximal classical development. Now you might there's an sort of an argument, there's sort of a basic question you may have. I don't know what's the way to say this. These initial data were odd. Why is there a preferred direction? And what is so special about the green curve versus the red curve? And so that's a long story that can only be sort of fully appreciated if you leave the class plane symmetric solutions and try to understand the picture in more general, which is, it's going to be a little bit the subject of today's discussion when we're leaving symmetry, but it's also going to be the subject of my lecture in the workshop next week. So there is something to be preferred about the green curve over the red curve, and it has to do with causal geometry, considerations of which surfaces are space-like, which surfaces are time-like. But it sort of requires a lot of scaffolding to fully describe what's going on, and I'm not prepared to do that at this point in the lecture. Let me just tell you that there is a preferred curve, and it is the green one and not the red one. And it has to do, at the end of the day, it has to do with the sign of the first derivative of mu. Sign of the first derivative of mu. Which, okay, if you take the first derivative of mu with respect to u, I should say, with the u of mu, you get 2u times t. 2u times t. And it turns out that to have a good solution theory, at least in the context of Euler, that derivative should 0 or negative. Okay, 0 or negative. So that means negative u values. You know, for t near 1, where we're seeing all of this singular behavior, negative u values, and negative u values corresponds to the green curve and not the red curve. Okay, but again, to sort of really appreciate this, you can't just look at transport equations. You have to look at the whole wave picture. You need to look at both directions and understand the causal character of these curves and surfaces. And you know, that's what I'll revisit in detail a little bit today and in my forthcoming lecture. Okay, so just a little bit of further discussion. So this is for this particular example, but the lessons learned from this example are important. So the time of first blow up, where this cusp lives, is 1. Okay, and if you look at the constant time hypersurface of first blow up, which I haven't drawn, it's just the flat line t equals 1, which, you know, what do you know happens at along that particular hypersurface, t equals 1? Okay, sort of, I want to understand that question in a more general setting, not just for this particular solution, but let's just pretend that t equals 1 is the time of first blow up. What do we know happens at the time of first blow up? We know that mu vanishes for the first time, and it's non-negative everywhere, because mu was supposed to be positive, you know, this inverse foliation density. And so wherever it vanishes, in other words, wherever you think there might be singularity, at the time of first blow up, mu has to be, if you fix that t and you look within that surface, mu has to be having a minimum value of 0. Okay, so minimum means that its derivatives in directions tangential to that surface. So in 1 + 1 dimensions, that would be d du only, has to be 0 because you have a minimum. And on the other hand, the Hessian has to be, the Hessian with respect to u, I should say, should be non-negative, because if it were negative, then, you know, you would Taylor expand and mu would decrease, and that's impossible because mu is not allowed to be negative. It has to be everywhere non-negative. And so this is basically a statement that holds for all solutions. You know, this argument works not just for this example, but for all solutions. So knowing that this holds, you may ask to yourself, what is the non-generic thing that happens at the vanishing points? And within the class of smooth functions, certainly the non-generic thing is that this second derivative with respect to u should be positive. Okay, and so that's a condition that we are calling transversal convexity. That if you take the question with respect to u and you restrict to the sets where mu equals 0, you restrict, this should be positive. Okay, and it's this condition that is it seems very important for understanding the formation of the singularity away from symmetry. if you don't have this condition, the problem looks very hard. That's not to say that it's not doable, but if this condition fails, if this were 0, if you were looking at non-generic solutions where this is 0, all sorts of crazy stuff can happen, and you can even see that in plane symmetry. So, for example, you can easily cook up initial data, even for this like simple model problem, where L r plus equals 0 and L is explicitly given by dt 1 plus r plus. You can cook up initial data easily, where at the first blow up time, the set of points where mu vanishes is not isolated. It's not a single point. It could be a line. It could be an interval. It could be a whole bunch of intervals. So if you're interested in the structure of the singular set, and I assure you that you would be interested if you were trying to construct weak solutions, you need to make some assumptions on the behavior of, to get your hands on the structure of the singular set. And if the singular set is bad, you should think that's basically the singular set, or if you want the set of points at the time of first blow up, where it was 0, can be arbitrarily complicated. It's just in TU coordinates, it's just the intersection of the level set of, or it's just a level set of some smooth function, intersected with sigma t, right? So that can have like really complicated structure, and it certainly doesn't have to consist of isolated points. Okay, and so you need some kind of assumption if you hope to understand what's going on away from symmetry. And transversal convexity is sort of the generic thing that you would like to assume to get. I mean, you can understand a huge amount under this. Let's call it a genericity assumption. So you can find initial data. You can find huge classes of initial data where this holds. This is a condition that is essentially propagated, at least for short times, by the flow. But I do want to point out that in general, without an assumption like this, the picture can be arbitrarily complicated. At this point in time, nobody has a full description of what the singular set might look like and how that affects the problem away from symmetry. It can be quite hard. Okay, so that's basically it for plane symmetry. And before I jump to the problem away from symmetry, I want to see if people would like to talk more about this picture, or if there are any questions. Okay. So yeah, maybe one more thing before we move on. I want to point out how different this is than the case of, let's say, vacuum Einstein equations. For vacuum Einstein equations, you have a uniqueness of maximal developments. So you might say, what the heck is the difference? Why is Einstein giving you uniqueness of maximal developments, whereas here looks like there's non-uniqueness? And here's the answer. The way we're thinking about the fluid problem, there's a fixed, rigid differential structure that you are forced into, and that is the differential structure of the Minkowski space. If you want the Tx1 differential structure that's given to you, you don't get to build the differential structure, that portion of the differential structure, as you go. That's given to you, and the fluid sort of lives in that differential structure, at least in the context of this problem. And you're stuck with it. It's nothing you can do about it. In contrast, if you look at how the development is constructed for Einstein equations, you're actually constructing the differential structure as you go. It's part of the process. You're just given some abstract. In the Einstein problem, you're given some abstract, codimension 1 manifold with initial data on it, and you want to construct the space-time, and that means constructing the differential structure to go along with it, right? So it's quite different here. And so, philosophically, that's the big reason why you can have non-uniqueness in these kinds of settings, but not for Einstein vacuum equations. Okay. So I'm going to jump to the problem away from symmetry, and just another quick recall. In isentropic plane symmetry, the relativistic Euler is a coupled system of transport equations, LR plus equals 0 and L bar R minus equals 0. Well, let me do something which seems inefficient. Let me take the L bar derivative of the first equation and the L derivative of the second equation. Okay, and then I get these two equations. So L bar L of R plus is 0 and L of L bar of R minus is 0. Okay, why do I write it like this? These are wave equations. That's why I write it like this. So in simple isentropic plane symmetry, as a consequence of the relativistic Euler, you can write down these wave equations. Okay, and you don't need to do this in but to get away from symmetry, it is very advantageous to take a wave point of view. Okay, very, very advantageous. And the reason is we have a lot of wave techniques. We have a lot of methods to understand solutions to geometric wave equations. And it's just so much easier to apply those techniques if you're already in a wave setup. Okay, and I mean, sort of one of the themes is that you can take relativistic Euler and you can differentiate it in a clever way, and you can end up with a very good wave system away from symmetry. Now, turns out that there are zillions of complications that come along with it, but philosophically, that's why you want to do this. You want to study, you want to put relativistic Euler into a wave framework so that you can use wave techniques. Okay, so about these wave techniques away from symmetry. If you want to understand singularities, shock waves, issues tied to maximal development for relativistic Euler, and you want to get away from symmetry, and you believe me that it's a good idea to think about wave problems, then you can already look at simple model problems. Well, they're not. Turns out they're not that simple. They're actually very, very, very rich. You can take, let's say, in 1+3 space-time dimensions, you can take a scalar wave equation, box of psi equals 0, where box is the covariant wave operator corresponding to a metric G, which is Lorentzian. And let's say with respect to standard coordinates, if you want, with respect to Minkowski rectangular coordinates, the components of the metric are assumed to be smooth functions of psi. So this is very close to what we have in compressible Euler. For compressible Euler, it's not a scalar problem. You have, these 6 unknowns that determine the flow, like the density and the entropy and the 4 components of the forward velocity. So it's definitely not a scalar problem, but it turns out that all of those scalar components solve wave equations with very interesting right-hand sides. And if you're interested mainly in understanding the singularity formation processes, then it turns out that all of the interesting stuff from the perspective of singularity formation happens on the left-hand side of the equation. And on the right-hand side of the equation are basically error terms that you work really hard to show are negligible. Okay, so remember box, if you expand it with respect to the rectangular coordinates, it looks like this. And if you see, you will get quadratic terms in the derivatives of psi. So like when d alpha falls on G is a function of psi. This gives you quadratic terms. And usually there's no good null structure associated to those terms when you expand things out. That's the generic thing, that you have nothing like a null condition. There's exactly this one equation of state that I time like a minimal surface equation where you do have a null condition. But for all the other equations of state, your favorite version of the null condition fails in this coordinate system. Okay.
Jared, could I ask a question?
Yeah, please.
So you say that essentially the right-hand side nonlinearities there don't matter too much. Is that a consequence of the type of analysis that you did? Somehow singularity formation is a result of the linear or of the quasi-linear structure, or is that because we just don't really know how to deal with nonlinearities on the right-hand side?
we do know how to deal with the actual nonlinearities that arise in relativistic Euler flow, in compressible Euler flow. It turns out that those nonlinearities which are present on the right-hand side are basically tiny error terms near singularities. So you can basically treat philosophically like they're zero. On the other hand, so this will help answer your question a little bit. If you write out box psi, you can introduce characteristic directions L and L bar, given your favorite Lorentzian metric in plane symmetry. So you can basically emulate what was done in Euler. If you write out, it's got the principal part. Let's say L bar of L derivative of something, but then you get the lower order terms. And so here is what they look like. Some function of psi times L psi squared plus some other function of psi times a cross term. Or you can switch the order here. You can put L on the L bar, and then you get something similar, some other function of psi times L bar psi squared, other function of psi times the cross term. Okay, and then here's the point. These red terms, they're quadratic in the L derivatives, and these are the terms that fail to satisfy the null condition. Okay, but they're all like swallowed up into the definition of box. You know what I mean? It's like okay, so these are the red terms are the bad ones.
Thank you.
If you want, and so you can basically now sort of repeat the analysis that I gave you for simple waves in the context of Euler and sort of reach all the same conclusions for this large family of wave equations. And so one of the things, that you can see sort of almost immediately is you can cook up initial data where L bar psi is initially large. Okay, and then this red Riccati term will create blow up. On the other hand, if you cook up for the same data, if it happens that L psi is small, okay, you can certainly do this. Cook up data where L bar psi is large and L psi is small. Then you do have a Riccati term in the L direction, but it doesn't have time to become, to blow up. If you integrate along the L bar direction, it doesn't have time to blow up. Bar psi squared blows up. So, this is the kind of game that you can play without even introducing characteristic coordinates or anything. But for this large class of wave equations, you can basically repeat everything I said for relativistic Euler in plane symmetry with the Riemann invariance and reach the same conclusions. Okay, so, but the main point is that you have these bad terms here generically, and they're hiding in the definition of box. And then the question is, when you're actually trying to treat relativistic Euler and you have zero, or if instead of zero, you have other things, how do you treat them? And it turns out that all of the other terms, effectively are not Riccati type. So you have lots of stuff, but none of them are like L psi squared or L bar psi like cross terms. And if you want to think that like L bar psi is the thing that's blowing up, then L bar psi squared is the dominant term, and stuff that's linear in L bar psi is going to be less important near the singularity, at least if you're treating solutions where L psi is going to remain regular. Okay, so it's the quadratic terms and the stuff that blows up that matter, and the claim is no other such terms on the right-hand side for relativistic Euler. You have a mess, but you have no other L bar psi squared terms. Okay, did that help?
Yeah, thanks. That was very comprehensive.
All right. So, so let me just give you some idea about things that have been done for the model problem or related problems. So you can prove small data blow up for the model problem. So Alinac followed the solution in the late 90s to the time of first shock formation. He considered data where you have only a single isolated point that blows up at the time of blow up. That's like a very strong version of the transversal convexity that I mentioned. He kind of had convexity in all directions if you want. Christodoulou gave a detailed description going way beyond what Alinac did for the irrotational relativistic Euler equations. That's his famous 2000 book. A few years later, he handled the non-relativistic case with Miao. And they basically gave a description of the formation of the singularity, And they followed the solution up to an interestingly large portion of the boundary of the maximal development. Okay, so I'll say more about that later, exactly what they did. He gave more information. He also produced, in the irrotational case, his result was actually very interesting. It was conditional global. So what he actually proved was that the only way a singularity can form in the small data regime in the irrotational case is through the collapse of the characteristics. That's the only possible singularity mechanism, small compactly supported of the non-zero constant states. And then he also, in addition to giving the conditional global existence results, he did give an interesting large set of data where the characteristics do impinge, and he described an interesting portion of the set of points in space-time where that impingement happened. Okay. And then inspired by Christodoulou's work, I did basically the same thing for all of the wave equations that were on the previous slide, basically all of these guys. Other people like Miao and Yu came along and treated different kinds of solution regimes. Like the Miao Yu result was a large data shock formation result for wave equations with cubic nonlinearities. With Holzagel, Luke, and Wall, we treated solutions that are near plane symmetry. So, this is the motivate. These wave shock singularities near plane symmetry from this paper are definitely behind some of the intuition that I was talking about earlier in the context of symmetric relativistic Euler. You can also prove, for these wave equations, you can prove low regularity well-posedness. So below the classical threshold, 5/2 plus whatever, where you can prove local well-posedness using only energy estimates and Sobolev embedding and so forth. To go below this, you have to use other techniques. And there are a lot of people that have contributed to this. There's a very sophisticated machinery. It relies on iconal functions and constructing the characteristics and understanding the regularity properties of the characteristics and their relationship to the decay of waves, and then ultimately the decay of waves and Streekart's estimates provides the mechanism for the local well-posedness. So that there actually is a connection with shock waves, because one of the things you have to do in this line of work is show that the characteristics are a good coordinate system for short times, and so you have to avoid the collapse of the characteristics, and so you have to control mu, or in their language, you have to control the null lapse under low regularity assumptions. Okay, so this is all stuff for the model problem and related equations. And again, the unifying theme is nonlinear geometric optics. So these iconal functions that depend on where the metric depends on the solution. Okay. So here's like the big idea. For some applications to fluids, especially ones involving iconal functions, you can treat the relativistic Euler equations as perturbations of the model problem. So again, you want to think that at least for some regimes and some classes of problems, relativistic Euler is just box psi equals stuff on the right-hand side, and you would like to treat the stuff on the right-hand side perturbatively. Moreover, if you're interested in perturbing known solutions, but allowing the perturbations to lack symmetry, so you want to treat general small perturbations of, let's say, known plane symmetric or spherically symmetric solutions, you can actually adapt the method of Riemann invariance. You have to supplement it with a lot of new ideas, but you can study the flow with something that basically plays the role of approximate Riemann invariance, and that's something we'll see later today. So these, like I said, relativistic Euler is a perturbation of a wave equation, and the same is true for non-relativistic Euler. It's a perturbation of a wave equation, and there have been results derived for those systems from that point of view, treating fluids as perturbations of wave equations. So I've done some low regularity work with Descanzi, Luo, Mazzone, and Qian Wang recently really sharpened it, pushed it to a more interesting regularity level. You can study the formation of shocks for, this has been done for non-relativistic compressible Euler. I did this in a couple of papers with Jonathan Luke. There is a different approach by Buckmaster, Scholar, Vikol that handles the case where you're first, at the time of first blow up, there's a unique isolated singular point. That's basically the regime that Alinek studied. But they did it for compressible Euler with vorticity, which is a much harder problem. And they actually use very different techniques coming from modulation theory, looking for self-similar solutions, and so on and so forth. This is a great result that they gave. I am, however, interested in results that give you the structure of the maximal development. And it's the only approach that is bearing fruit so far for that problem is the approach that's based on iconal functions, so nonlinear geometric optics. Once you know that a singularity is formed, a shock singularity, of course, you would like to solve past the shock, uniquely, weakly. Christodoulou and Lizebach have done this in spherical symmetry for the relativistic Euler equations. Now, this is the paper that I mentioned earlier where you can read about the Riemann invariance. In that paper, they solved past the shock for short times using a weak formulation of the flow. And it's a really nice paper. It's really long, but there's a lot of powerful ideas in it that I don't think have been applied to other problems, but they could be applied to other problems. Then Christodoulou had this fantastic monograph in 2019. This treated the relativistic and non-relativistic equations, fluid equations at the same time. He said density and entropy artificially equal to 0, however. That's called the restricted shock development problem. And basically what Christodoulou did in that book was solve for short times past the first singularity weakly without symmetry. But if you actually look at the weak formulation of fluid flow, even if you start with an irrotational solution with constant entropy, after the first singularity, the weak solution will develop dynamic entropy and the vorticity will jump and become non-zero. So this is the famous claim that the entropy should jump across the shock hypersurface and the vorticity should jump. That happens in the real problem. Christodoulou ignored that in his book. It's a very interesting open and hard problem. I think he's working on it right now. But in any case, the fact that he avoided symmetry assumptions, was definitely qualifies it as a breakthrough in my mind. And he coined this the restricted shock development problem. And last summer, Buckmaster, Drewes, Scholar, Vikol, they did compressible Euler with vorticity in a symmetry class, where you can study it with transport techniques, transport equations. And they have the first short time shock development result with vorticity. Okay, so those are the results to keep in mind that are sort of motivating the way I'm thinking about fluids. Now, the non-relativistic results that I named up here, they rely, except for the work of Buckmaster, Drewes, Scholar, and Vikol, they rely on new formulations of the equations. Okay, and in the non-relativistic case, I wrote these down with Jonathan Luke, and in the relativistic case, I wrote them down with Marcello Descanzi. And the short version of the story is that there's a similar structure here. Basically all of the same structures one sees in the new formulation. In the non-relativistic case, they basically seem to be present. In the relativistic case as well, sometimes there's some additional complications that occur in the relativistic case, but the basic structures remain intact. And it's my firm belief that basically all of the non-relativistic results should carry over. Doesn't mean they're easy problems, doesn't mean that they're bad problems to work on, especially for like a student or someone trying to learn the field, but I do believe they should essentially carry over. Okay, and at the end of the day, what does the new formulation, what does it give to you? You can exploit the geometric vector field method to the nth degree. And I know that's, people in this audience know and love that method because it's given so much. And, I guess it's good news that the same method is so important in the context of shock waves. Okay, now what's the long-term goal? Of course, you want to understand spatially and temporally global solutions to the fluid equations that are piecewise smooth and have shocks in them. And even better if we can couple it to the Einstein equations and say something about the coupled problem. Okay, but those are really hard problems. And but that's what one is working towards. Okay, so before I show you what the new formulation of relativistic Euler looks like, at least I'll give you some schematic depiction of how to think about it. So you do have a wave equation, so you have a covariant wave operator on the left. For relativistic Euler, this G is nothing other than the acoustical metric, the same acoustical metric from yesterday. And instead of box I equals 0, you have basically three kinds of terms that you have to worry about. The first is null forms, which end up being harmless because there are no Riccati terms present in null forms. There's no L term. There's no L bar psi squared term. So it's important that these are G null forms. I'll say a little bit more about that in a second. And then you have terms that are questionable from the point of view of regularity. And so this is where all the hard work comes in. You have like something like a curl of a vorticity and a divergence of the gradient of the entropy. And if you are not very careful, it looks like these terms will lose regularity. Okay, this is the, as written, it looks, if one takes a close look, it, looks like, oh no, I'm losing one derivative. I can't really treat this like a wave equation, but fortunately there's a way around that, okay? And, the upshot is, at least in the context of singularities, these terms will all end up being perturbative, but the precise nonlinear structure matters. The exact details are important. So these null forms, such as, so here's an example of what I'm calling a G null form. So why do I call it a G null form? So it's really important that in this null form, G inverse alpha beta d alpha psi d beta psi, that this is really the fluid metric, the acoustical metric. In other words, you cannot add cubic terms. This theory is very unstable under perturbations of the equations. In some problems, like small data global existence problems, you can put whatever dt psi to the 10th power on the right-hand side as a perturbation, and in a global existence problem, that will not matter. But in a problem where something is becoming singular, if something is becoming singular, and you add dt psi to the 10th to the right-hand side, then near the singularity, that large power of dt psi is going to be dominant. So, and what I said is true not just for really high powers like 10, but it's also true for cubic terms and quadratic terms. You can't just throw your favorite cubic or quadratic term on the right-hand side and expect the theory to survive. It does not. So here, it's important that this is exactly, the kinds of terms that you get in the equations are really null forms with respect to G, and that you don't have cubic error terms that are cubic in the derivatives of psi that become dominant near the shock. You really have something special going on. And as I mentioned, you're going to have to deal with some derivative loss. And there's a way around that, and it involves some new structures that I found with Luke and Descanzi, and more recently with Leo Abreschia. How do you avoid the derivative loss? The short version of the story is that there's something like div curl transport systems for the vorticity and entropy. So there's an additional structure that for these terms, you can gain an extra derivative on them by studying like a Hodge system, div curl, but it's not really a Hodge system. It's like a transported Hodge system. And the transport part of the flow has a good null structure. So you basically have these null forms. So basically everything good happens. Okay. So before I get into those details, let me show you a picture of things that are in the process of being proved, written down. I will discuss this picture in more detail in my lecture in the workshop. So basically, this is what is, so I have a paper coming out, it's actually two papers coming out with Leo Abreschia. It's about what does the maximal development look like for compressible Euler. for perturbations without symmetry of plane symmetric solutions. Okay, so this, even though our paper concerns non-relativistic Euler, I have no doubt that the same picture holds in the relativistic case. Of course, this is without coupling Einstein's equations. Okay, and then, so here's what's going on. So this is a 1 + 3 dimensional problem with initial data given on sigma 0. This is like a flat sigma 0 piece, although it doesn't have to be a flat sigma 0 piece. Time is vertical as usual. The x1 direction is exactly the same as in plane symmetry. And now what about the directions that break the plane symmetry? Well, we could have chosen R2, like x2 and x3 live in R2, but we just prefer to deal with the 2 torus because it simplifies some technical parts of the analysis. And it's a local finite speed of propagation problem anyway, so it doesn't really matter what your topology is if you're only interested in local considerations. Anyway, so that's the picture. And then you should imagine that, in the x1 direction, you have something that's basically looks a lot like it looked in plane symmetry. And then the question is, how do you deal with these other directions? Okay, how do you deal with the, and so this is the work with Leo Abreski is going to come in 2 flavors. It's going to be 2 papers. The first paper is constructing B. This is the singular boundary of the maximal development. And the second paper is constructing C bar. This is the Cauchy horizon. So in this framework, the singularity is this codimension 2, spacetime codimension 2 submanifold, which we are calling the crease. This is an analog of the cusp from plane symmetry. And this red surface called B is basically the set of points in the maximal development where you have something blowing up. The first derivatives of the fluid blow up because of a shock. And I'm not showing the characteristic hypersurfaces in this picture, but basically they're piling up along the singular boundary. And that's resulting in a singularity. And one of the great degeneracies of this problem is that this singular boundary B is foliated by integral curves of a null vector field called L. So in a certain sense, the singular boundary is also a null hypersurface. So it's a very borderline delicate kind of object. It's even at the border of what you could hope to control from the point of view of well-posedness and energy estimates. I mean, you can hope to do something along a null hypersurface, but there's no way that you can hope to get sort of an estimate along a time-like hypersurface. This carries a moral warning to you that if you are trying to derive these pictures, there's basically no hope of trying to solve the problem using only predetermined coordinate systems. Really everything has to be adapted to the flow. If you're going to sort of construct null hypersurfaces, that's part of the problem. These are not background objects. Okay, and then the other thing, so this is the will be the coming from the second paper is the construction of a Cauchy horizon, where you don't have a singularity. Okay, the Cauchy horizon shoots out of the crease, the first singularity if you want, but the fluid does not blow up here. This has to be removed from the spacetime because it emanates from the singularity. And finally, so I see we're getting close to the point where a break was taken yesterday. So maybe I'll just say a few more words and then ask if people want to take a break. Okay, what about this hypersurface K? Okay, this has not been constructed for the full problem yet. This is the problem that Christodoulou is working on. So, as it turns out, when you have a first singularity, which is, again, this is this code dimension 2 submanifold called the crease. When you have a first singularity and you impose the weak formulation, so this is the key, you impose the weak formulation.
Move mouse up.
I'm sorry, James, what was that? Sorry, I thought I heard a question. When you impose the weak formulation, which is a choice, you choose to impose the weak formulation. It introduces a new speed of propagation into the problem, and that is the speed of the shock hypersurface itself, called K. Okay, and K if you impose the weak formulation and solve the problem, which again, it hasn't been solved yet, aside from the restricted problem and problems in symmetry, there will be a jump across the surface K. Okay, the fluid will jump, basically the density will jump a little bit across K. The jump is 0 at the crease and it grows as you head out along K. Goal of solving the shock development problem is to construct K, solution on either side of K. And as it turns out, there's a weak solution on either side of the Cauchy horizon as well. So basically the initial data, if you want, the starting point for the shock development problem of constructing a weak solution is the behavior of the solution on a Cauchy horizon. And the behavior of the solution in the vicinity of the singular boundary. So, to be very clear, something interesting happens. The singular boundary is not part of the weak solution, except the crease. When you construct the weak solution, it will agree with the classical solution up to K, but then the solution will jump across K, and you will get a weak solution that disagrees. So in between K and B, you will have two solutions that disagree with each other, the weak one and the classical one. So you might say, why do I care about the maximal classical development if this little piece is not even going to be part of the weak solution at the end of the day? Well, the two reasons. So first of all, the Cauchy horizon is part of both solutions, so you definitely need this piece. The second reason is when you actually go to construct K using the known approaches, you actually need information in a neighborhood of K to run the iteration arguments. So the surface B up here kind of serves like a barrier in the actual construction. And something that's very interesting is that K starts off tangent to B. If you want, like the separation goes to 0 near the crease. So like K is, you may think it's an asymptotically null surface. So basically to set up properly the problem of just to set up the initial conditions for the shock development problem, you essentially need to understand this whole picture. And the short version of the story is that this picture has not been fully understood in this solution regime yet, or even any regime as far as I can tell. Okay, so but I'll say more about that in my workshop lecture. Perhaps now is a good time to take a little break